Assalamualaikum warahmatullahi wabarakatuh. So, our group want to present about group assignment for subject MAT 652 Algebra Structure, and we are from group CS 2495A. This is our group members, which is Muhammad Arfikri bin Muryadi, Muhammad Faizal Aiman bin Abdul Rahman Muhammad, and Muhammad Syahdini Azri bin Muhammad Sufyan.
Okay, for the question number one, let H be the subset of matrix consisting of all matrices of the form A minus B, BA such that AB is element of R enclosed under both matrix addition and multiplication. Let H is a metric representation of the complex number C and R is a real numbers. Show that C plus is isomorphic to H plus and C dot is isomorphic to H dot. Okay, for the question number one, there are four steps to show whether it is isomorphic or not. Okay, for the step one, define the function. Phi C arrow H as phi A plus BI equal to matrix A negative B BA. And next, for the step number two, show that phi is a one-to-one function. Suppose phi A plus BI equal to phi C plus DI, then matrix A negative B BA is equal to C negative D DC. Since A equal to C and B is equal to D, it shows that A plus BI is equal to C plus DI. Thus, phi A plus BI is a one-to-one function. Okay, next, for the step number 3, show that phi is onto. If M element H, then M is equal to matrix A negative B BA for some AB element of R. Hence, for A plus BI element of C, phi A plus BI is equal to matrix A negative B BA is equal to M. Thus, phi A plus BI is onto. Okay, for the last step, show that phi A plus BI plus C plus DI is equal to phi A plus BI plus phi C plus DI. Thus, phi A plus BI plus C plus DI is equal to phi A plus BI plus phi C plus DI. Therefore, phi is satisfied homomorphism properties. Okay, therefore, C plus is isomorphic to H plus. Okay, for question 1b is also same with question 1a, which is to show whether it is isomorphic or not. They also have four steps to show it. Okay, the step 1 is define the function. Phi C arrow H as phi A plus BI is equal to matrix A negative B BC. Next for the step number 2, show that phi is a one-to-one function. Suppose phi A plus BI is equal to AC plus DI, then matrix A negative B BC is equal to C negative D DC. Since A is equal to C and B is equal to D, it shows that A plus BI is equal to C plus DI. Thus, phi A plus BI is a one-to-one function. Okay, next for the step number 3, show that phi is onto. If M element H, then M is equal to matrix A negative B B C for some A B element of R. Hence, for A plus BI element of C, phi A plus BI is equal to matrix A negative B BA is equal to M. Thus, phi A plus BI is on 2. And for the last step, show that phi A plus BI multiply with C plus DI is equal to phi A plus BI multiply with phi C plus DI. Thus, phi A plus BI multiply with C plus DI is equal to phi A plus BI multiply with phi C plus DI. Therefore, phi is satisfied homomorphism properties, so that C dot is isomorphic with H dot.
Now we go to the question 2. For the question A, when discussing residual classes, one is not well defined until the modulus n is given. Explain. So the solution for this question, first definition of residual class. A residual class modulo n is a set of integers that are congruent to each other under modulo n. Specifically, the residual class of an integer a modulo n denoted a mod n is defined as a mod n equal to x element of z, which is x equivalent to a mod n. Second, role of the modulus. The modulus n determines the equivalence relation on the set of integers. Two integers a and b are considered equivalent under this relation if a equivalent to b mod n or n divide to a minus b. Without specifying n, we cannot determine whether two integers are equivalent, as the definition of equivalence depends on n. Alright, now we go to the third one. Ambiguity of the residue class of 1. The residue class of 1 modulo n, denoted 1 modulo n, represents all integers that are congruent to 1 modulo n. For example, for n equal to 5, the residual class of 1 modulo 5 is negative 9, negative 4, 1, 6, 11, and so on. For n equal to 7, the residual class for 1 modulo 7 is negative 13, negative 6, 1, 8, and 15, and so on. As seen from this example, the actually elements of the residual class 1 modulo n change with the modulus n. Yeah. The four is well defined. When we say a residual class is well defined, we mean that it is uniquely determined. However, without the modulus n, the statement the residual class of 1 is ambiguous because it does not specify which modulus is being used. The residual class of 1 modulo 5 is different from the residual class of 1 modulo 7, and so on. Therefore, specifying the modulus n is essential for the residual class of any integer, including 1, to be well defined. Without n, the context of which integer are considered equivalent to 1 is missing, making the concept incomplete and ambiguous. Now, we go to the question B. Determine whether the given relation is an equivalence relation on the set if n relation m in Z and nm greater than 0. So the solution is to determine whether the given relation R on the set Z, the set of all integers defined by n relation m, if and only if nm greater than 0 is an equivalent relation, we need to check if it satisfies the three properties of an equivalence relation, which is reflexivity, symmetry, and transitivity. For the first one is reflexivity. A relation R on a set A is reflexive if for every A element of A relation A holds. For n relation n to hold, n greater than 0 must be true. This means n square greater than 0. This is true for all n in Z except n equal to 0. Since 0 relation 0, otherwise 0 multiple 0 equal to 0 is not greater than 0. So the relation is not reflexive. And the second one is symmetry. A relation R on a set A is symmetric if for every AB element of A where A relation B implies B relation A. If n relation M, then Nm greater than 0. This implies that M relation N since Mn equal to Nm greater than 0. Therefore, the relation is symmetric. The third one is transitivity. A relation R on a set A is transitive if for every A, B, C element of A where A relation B and B relation C implies A relation C. For example, if N relation M and M relation L, then the Nm greater than 0, Nml greater than 0, we need to show that Nl greater than 0. If n m greater than 0, n and m must have the same sign, which is both positive and both negative. Also, also, if ml greater than 0, m and l must have the same sign, which is both positive and both negative. Since m has the same sign in both nm greater than 0 and ml greater than 0, N and L must have the same sign as well. Thus, NL greater than 0 and N relation L holds. Therefore, the relation is transitive. Since the relation is not reflexive but is symmetric and transitive, it does not satisfy all the necessary conditions to be an equivalent relation. Therefore, the relation R defined by n relation M if and only if nm greater than 0 is not equivalence relation on Z. Now we go to the question C. Prove that if star is an associative and commutative binary operation on a set S, then open bracket A star B close bracket star open bracket C star D close bracket equal to open bracket D star C close bracket star A close bracket star B for all A, B, C, D element of S. Assume the associative law only for triples as in the definition. That is assume only open bracket x star y close star z equal to x star open y star z close bracket for all x, y, z element of S. Okay, so for the solution, we go to the next slide. Now, the solution for the question C, which is we want to prove whether it is commutative or not. So, for all A, B, C, D element of S, for the left hand side, we have open bracket A star B close star open bracket C star D close bracket equal to open bracket D star C close star A close bracket star B. Alright, so for the right hand side, we have open bracket C star D close star open bracket A star B close equal to B star open bracket D star C close star A. And then we solve, and at the end for the right hand side we got open bracket D star C close star A close bracket star B. Since left hand side equal to right hand side, therefore star is commutative. Next, we want to prove whether it is associative or not. And then for the left hand side, we have open bracket A star B close star open bracket C star D close star open bracket E star F close equal to open bracket D star C close star A close star B close bracket star E F. And then at the end for the left hand side we got open bracket D star C close star A star E close bracket star B star F. And for the right hand side we have A star B close bracket A star open bracket C star D close bracket star open bracket E star F close equal to AB star open bracket D star C close star E close bracket star F, and then we solve. And for the right hand side we got open bracket D star C close star A star B close bracket star B star F. Since left hand side equal to right hand side, therefore star is associative. And then for the last one is for all x, y, z element S. And for left hand side, we have open bracket x star y close star z close bracket star AB equal to x star open bracket y star z close star AB. And then we solve. And for the left hand side, we have equal to x star A star open bracket y star z star B close. All right. So for the right hand side, we have open x star y close star open AB star z close bracket equal to open bracket x star y close star open bracket z star open bracket A star B close. And then after we solve, and we got for the right hand side equal to x star A star y star z star B. And then since and a left hand side equal to right hand side, therefore star is associative.
Question 3. Let G dot be a group. Consider the binary operation star on set G defined by A star B equal to B dot A. For all A B element G, show that G star is a group and that G star is actually isomorphic to G dot. Consider the mapping phi with phi A equals to A prime for all A element G. First, we need to make sure that G is closed under the binary operation. We let A be element G and consider A star B. According to the definition of star, A star B equals to B dot A. Since B dot A element G, A star B element G also. Thus, G is closed under binary operation. First thing first, we check the associativity of the binary operation. For all A, B, C element G, show that A star B star C equals to A star B star C. We look at the left hand side first. A star B star C is equal to B dot A star C, which is equal to C dot B dot A. Since dot is multiplication, we rearrange it and become ABC. Next, we move to right hand side. A star B star C equals to A star C dot B becomes C dot B dot A. We also rearrange it and become ABC. Since left hand side is equivalent to right hand side, therefore the binary operation is associative. Next, we check the identity element of A. For all A element G, there exists E element G such that A star E equal to E star A equal to A. We take the equation from the definition, which is E star A equal to A dot E equal to A dot AE equal to A. We move A to the right hand side and we get E is equal to 1 element of G. Since 1 since E equals to 1 element G, therefore the binary operation is satisfied the axiom 2. Lastly, we check for the inverse. By definition, for every A element G, there exists A inverse element G such that A star A inverse equal to A inverse star A equal to identity. We take from the equation from the definition, A inverse star A equals to E. Since E equals to 1, we substitute it into the equation and become A inverse star A equals to 1. A dot A inverse equals to 1. A inverse equals to 1. We move A to the right hand side and become A inverse equal to 1 over A. Since there exists an inverse, therefore, binary operation satisfied axiom 3. Since the binary operation satisfied all axioms, therefore, G star is a group. Show that G star is actually isomorphism to G dot. First thing first, we have to define the function. Phi G star implies G dot such that phi A equal to A inverse. Next, we move to the first axiom, which is 1 to 1. We let A be element G, then phi A equal to A inverse and phi B equal to B inverse. If phi A equal to phi B, then A inverse equal to B inverse. We take the inverse for both sides and become A inverse inverse equal to B inverse inverse, and we get A equal to B. Therefore, phi A equal to A inverse is one-to-one function. Next, we move to second axiom, that is on 2. For every n element G, hence n equal A inverse element of G, then A equal to n inverse element of G. Then phi A equal to phi n inverse equal to n inverse inverse equal to n element G. Therefore, phi A equal to A inverse is onto. Lastly, we check the homomorphism. Let phi A equal to A inverse and phi B equal to B inverse. Show that phi A star B equal to phi A dot phi B. We start from the left hand side to become the right hand side, which is phi A star B equal to phi B dot A. By using the inverse property in a group, B dot A inverse become A inverse dot B inverse. This is become phi A dot phi B. Since phi A star B equal to phi A dot phi B, therefore phi A equal to A inverse is homomorphism. The conclusion is phi A equal to A inverse is an isomorphism.
For question number 4, there are three questions which is A, B and C. Okay, I read the question. Let R and S be positive integers. For question A, define the least common multiple of R and S as a generator of a certain cyclic group. And for the question B, under what condition is the least common multiple of R and S equivalent to their product Rs? And last question, Generalizing part B show that the product of the greatest common divisor and the least common multiple of R and S is Rs. Okay, for solution for 4A, assume that we represent the smallest positive integer that is divisible by both R and S as LCM Rs, which is the least common multiple LCM of R and S. A cyclic group can be produced by one element, and if the LCM is a generator, then powers of the LCM can construct all the elements in the group.
Solution for B. The least common multiple LCM of two positive integers R and S is equivalent to their product Rs if and only if R and S are coprime, meaning they have no common prime factors other than 1. LCM Rs is equal to Rs if and only if GCD Rs is equal to 1, where GCD-RS denotes the greatest common divisor of R and S. The LCM of R and S is given by LCM-RS is equal to R dot S over GCD-RS. For LCM-RS to be equal to R dot S, the denominator GCD-RS must be 1. So, from the equation, we have to prove that GCD-RS is equal to 1. Condition for LCM-RS equal to R dot S. We substitute LCM-RS with previous equation and we get R dot S over GCD-RS equal to R dot S. We simplify this equation and we get GCD-RS is equal to 1. Since GCD-RS equal to 1, therefore LCM-RS is equal to RS.
Alright, now we go to the solution for the question 4C. H equal to NR plus MS, where N, M is element of Z. Under addition is the greatest common divisor of R and S. We write D equal GCD RS. The product of the greatest common divisor GCD and the LCM of R and S is always equal to the product of R and S, RS. Therefore, if the GCD RS equal to 1, then R and S are coprime and the product of their GCD and LCM is equal to RS. So that's all from our group. Thank you. Bye bye. Assalamualaikum warahmatullahi wabarakatuh.